So, we are back into our lecture series on advanced hydraulics. So, this we are going through the third module of the lecture series. The third module, it is titled as varied flows. If you have gone through the syllabus, you will know that. So, today is the third lecture of this module, and we can give the title of today's lecture as gradually varied flows and its classifications. So, definitely the classification, the entire classification of the gradually varied flow may not be able to be completed today in today's lecture alone. So, there will be a next part in the following lecture as well. In the last class, we discussed on varied flows in open channels. The various types of varied flows that were suggested, the gradually varied flow, rapidly varied flow, spatially varied flow, etc. These things we have just briefly discussed. We have not gone through the technical discussions on those aspects. Definitely, but however, we have introduced to you the a particular type of varied flow, that is the gradually varied flow. This we suggested that it is a non-uniform flow in open channels, and it is also having a steady state condition. That is, the flow conditions in the channel are not changing with respect to time. Even though the flow is non-uniform, but that non-uniformity is maintained, that particular the varied non-uniformity it is maintained completely throughout the time. So, we also had applied the conservation of mass principle to gradually varied flow, and you have seen how the continuity equation will look in the gradually varied flow. Also, we have discussed on the application of conservation of momentum principle to gradually varied flow. That is, these principles were used to develop the dynamic equation for gradually varied flow. If you have gone through that, see, the slope of the water surface dy by dx is equal to S 0 minus S 2 by cos theta minus beta m q square t by g a cube. The terms S 0 is the bed slope, S 2 is the shear slope, q is the steady discharge in the gradually varied flow, t is your channel top width, a is the area of cross section, theta is the angle the channel bed makes with the horizontal. So, all these things were discussed in the last class. We had also developed the dynamic equation for gradually varied flow using conservation of energy principle. There also you had derived this particular portion, slope of the water surface dy by dx is equal to S 0 minus S e. So, here the S e term is being used, that is the energy slope is being used, and also you have used the correction factor as the kinetic energy correction factor alpha. So, these some of the differences, this means that how the dynamic equation differs in energy as well as momentum equations. If you apply it in energy equation, it will look like this. If you apply it in momentum equation, it will look like this. So, there are quite some differences, that is, the differences quite obvious are momentum correction factor versus kinetic energy correction factor. So, whatever difference are there in these correction factors, that will be reflected when you compute your slope of the water surface. Another obvious change you can observe is shear slope versus energy slope. So, if these things are quite different in a particular channel, then obviously your results will the water surface slope, that will also differ when you compute the water surface slope, or if you compute the water surface these things and all using these dynamic equation, the results will be quite different in both if you use the two different equations. So, what we have to do is that we can make certain assumptions. That is, if you incorporate certain assumptions in the dynamic equation, just for a simple situation, in a simple cases that we are considering prismatic channels. Suppose if you are taking a rectangular channel, or if you are taking a trapezoidal channel, or if you are taking a well designed prismatic channel, the entire reach of the channel, if it is prismatic, then some of the assumptions that can hold good for such situations are, you can have, say, if you incorporate some assumptions, if you incorporate certain assumptions, then dynamic equation for gradually varied flow using momentum and energy principles can be unified. So, what are those assumptions? Say, if you assume that the momentum correction factor beta m is almost equal to your kinetic energy correction factor alpha, and if they are almost equal to 1, say we are approximating it as 1 if there is no significant correction factors involved. So, this suggests that the velocity distribution, so that is the velocity distribution across a cross section is fairly uniform. So, if we can incorporate this assumption, also another assumption we can suggest is that if the shear slope S tau, if it can be approximated as energy slope, both of them can be approximated as the friction slope S f. If we can do that, then further means it will help us in further unifying the dynamic equations of gradually varied flow. So, we can see that is friction slope is the one which is used in Manning's equation. If you use the Manning's equation and all, you can suggest that the friction slope S f is nothing but equal to n squared q squared by a squared r to the power of 4 by 3. One can also think of using Chassis equation, but I am not going to discuss it here. So, by this way one can use the friction, so one can compute the friction slope, and if you can approximate your shear slope and energy slope with this friction slope, well, good, you can directly substitute them in the dynamic equation. Also, we are suggesting that the bed slope of the channel is very small. We are suggesting that the bed slope of channel is very small. That is, this approximation is used such a way that we are suggesting cos theta is approximately equal to 1. So, if we incorporate these three assumptions, your dynamic equation for gradually varied flow becomes, your dynamic equation for gradually varied flow becomes dy by dx is equal to S 0 minus S f by 1 minus q square t by g a q. Fine. So, you have the dynamic equation now unified, both using the conservation of energy as well as conservation of momentum principle. By applying those assumptions, we are able to unify the dynamic equation, and you are getting it in a much simplified as well as a better form. How will you tackle if you have given this dynamic equation? Now, what is the purpose? How will you try to understand the equation now in a physical way? What does this mean? You just recall. You recall from the module 1, recall from module 1, we discussed on critical flows, right? Critical flows in open channel. You had discussed them, if you recall them. At that time, we had suggested that the following quantity q squared T c by G A C Q, this will be equal to 1 for critical flow. This will be equal to 1 for critical flow, if you recall them, right. So, where T c is the top width for critical flow, AC is the area of cross section for critical flow. So, entire quantity, if you recall them, this was almost related with the fluid number also, this entire quantity, and this for critical flow, this quantity is equal to 1. This particular quantity, we suggested that this is equal to 1. So, if we have these things, if you recall them, now it is quite easier if you incorporate the similar principles now in the dynamic equation for gradually varied flow and all, it will be quite easier now. So, for the specific energy in module 1, you discussed that this is nothing but the pressure head plus velocity head, right. This is y plus q squared by 2 g a squared. So, before deriving specific energy in that class, you had also suggested that total energy head H is equal to datum head plus pressure head plus 2 g, right, where z is your datum head. So, what does this mean? So, from these things, it is quite obvious that your energy, specific energy E is nothing but total energy minus datum head. Okay. That is E is equal to H minus Z. Therefore, dE by dx, if you go along the reach of the channel, that is in the flow direction, dE by dx, this means that this is equal to dH by dx minus dZ by dx. So, if you have the channel bed like this is your datum line. So, if you proceed in the x direction, this is Z1, this is Z2, datum head at 2 locations. So, this is the energy line, water surface line, right. So, what does this mean from these things? dz by dx, this quantity dz by dx, this gives you the slope of the bed, right. It gives a, or say, what does this mean? Here the height is z1, here the height is z2. So, the height or the datum head, it is decreasing in the x direction. So, dz by dx gives you the slope. So, we have already discussed this thing. It is the negative minus S 0. We have to give it minus S 0 because the datum head it is decreasing in the flow direction. dH by dx, this is your energy slope, that can also be given here SE or SF. If you recall that we have approximated energy slope with the friction slope and all. So, dH, so it is SF. Therefore, you get dE by dx quantity as S0 minus SF. So, why we suggested these things here is that in your dynamic equation, the numerator consists of S0 minus SF term. So, the numerator term is actually suggesting the slope of the specific energy, right. So, you can think in that direction, we can further evolve these equations, further try to proceed them. So, the dynamic equation for gradually varied flow S0 minus SF by 1 minus q square T by G A Q. So, as suggested earlier, for critical flow q square T c by G A C cube is equal to 1, or q squared by G is equal to A C cube by T. This is for critical flow, right. For critical flow, q squared G by is equal to A C cube by T. In that class, at that time we had suggested a quantity called section factor Z. In module 1 we have discussed these things, section factor Z. This is nothing but for section factor Z for critical flow, let us give it as ZC. This was given as AC cube by TC root. So, in the critical flow equation, the right hand this particular term, this is nothing but the square of your section factor, right. So, ZC this was defined in those portions. So, here again you can use them. So, for any other flow, not only critical flow, you can define section factor. You can define section factor. This is nothing but equal to the corresponding cube of area by top width. The whole thing you have to square root it. It is Z is equal to root of A cube by T. Like this one can define that. So, again I am going back to the dynamic equation now, S 0 minus S f by 1 minus q squared by G, and just look into the equation. This particular portion T by A cube, this is nothing but your section factor for the channel at that for that particular flow. What is the section factor for the channel? That is being given by T by A cube, isn't it? So, I will just substitute those things now in the equation. So, this is q squared by G into 1 by Z squared. Now, what is q squared by G? Go back to the previous slide. Q squared by G, this is nothing but equal to the square of the section factor for critical flow. that is q squared by g is equal to z c squared. Just go back again here, q squared by g is equal to a c cube by t c, and z c, this is z c is given by a c cube by t c, the square root of that. So, substitute this thing. Now, this is q squared by g, you can substitute those things. So, you will get the following relationship. Therefore, your dynamic equation becomes dy by dx is equal to S 0 minus S f by 1 minus Z c by z whole square, right. So, now you see we are just trying to further simplify the dynamic equation in terms of certain non-dimensional or some certain parameters like conveyance factor, section factor and all. So, here we use the section factor. Now, in module 2, you had discussed the uniform flow. In uniform flow, uniform flows were discussed. Manning's equation it was given as 1 by n r to the power of 2 s naught to the power of half, or q is equal to 1 by n a r to the power of 2 by 3 s naught to the power of half. That means, this is equal to some conveyance factor k n, right, into s naught to the power of half, where conveyance factor is equal to 1 by n a r to the power of 2 by 3. If you know this thing, so now in the uniform flow, if your discharge q, if it is following a uniform flow pattern, it can be easily written in the following form. In gradually varied flow, we suggested that the friction slope S f, it has to be computed using Manning's equation, and you have to use the parameters, that is the hydraulic radius as well as the area of cross section at that particular point, at that particular section, what is the corresponding value of A and R, you have to substitute them and identify the this thing. So, you identify the friction slope. So, this was given in the following form: r to the power of 2 by 3, or S f is equal to V squared n squared by r to the power of 4 by 3. So, now you have expressions, that is S f, expressions for S f, you have expressions for S naught also here. S naught you can easily think now in this following term. Therefore, S naught is equal to q squared by k n squared, right. So, that thing you can think in that terms now. If for any flow, that is not only uniform, if we apply the Manning's equation and if you see that your discharge Q, it can be computed using a conveyance factor K into the friction slope, the square root of the friction slope. If we can devise like this, now this is the conveyance factor. Okay. This is your conveyance factor. So, what does this, if we, this is just a empirical relationship which we suggested, formulated, means as we stated it here. Here you have suggested that this entire quantity can now be called conveyance factor in the uniform flow. Similarly, in the other types of flow, you can suggest the discharge Q is equal to some conveyance factor K into the square root of the friction slope S f. Like that, if we can do that, one can easily now derive your S f or your energy slope, friction slope. This is nothing but Q squared by K square. So, therefore, you also have S 0 is equal to Q squared by K n squared. That is, only in the case of uniform flow you have bed slope equal to friction slope. Okay. So, S 0 minus S f, this is now equal to Q squared into 1 by K n squared minus 1 by K square. So, what is Q squared by K n square? That is nothing but your bed slope, right? Q squared by K n squared is nothing but. So, if I can take that out, Q squared by K n squared, if I take it as a common thing. So, what will remain here? 1 minus K n by K whole square, like this you will get. So, S 0 minus S f is nothing but S 0 into 1 minus K n by K whole square. So, you got the numerator of your dynamic equation in the following form. It is quite easy now. So, therefore, your dynamic equation becomes dy by dx is equal to S 0 into 1 minus K n by K whole square by 1 minus Z c by Z whole square. So, your dynamic equation, I have now represented it using conveyance factors and section factors. Why I use this thing is that by knowing the conveyance factor, by knowing the sections factor and all, you will be easily able to identify using the depth of flow or based on the depth of flow and all, what type of gradually varied flow is there. This relation can now be used for classifying the gradually varied flow profiles, that is coming as a subsequent part of this lecture. We will see that. So, I can now write it as, say, classification of gradually varied flow profiles. Fine. So, if you recall the last day's lecture, we had suggested at that time called gradually varied flow, like say backwater curves, drawdown curves. If you recall them, we suggested that for any gradually varied flow, if the water surface decreases, if the height of the water surface decreases in the flow direction, then it is called drawdown curve. If the height of the water increases, then this is called backwater, the water surface curve is called backwater curve. right. So, the same thing, how can you identify now? So, if in the dynamic equation the dy by dx quantity, if this is a positive term, what do you mean by positive? That is, the slope of the water surface, it is increasing. We are not talking about the height of the water surface. If the slope of the water surface, if it is if it is a positive value, then that will give you the backwater curves, right. You look at this backwater curve, the slope dy by dx, it becomes positive here. Similarly, in the drawdown curve dy by dx, if it is negative, then that will give you drawdown curves, fine. So, what are the conditions now? Look into the dynamic equation, dy by dx is equal to S 0 into 1 minus k n by k whole squared by 1 minus z c by z whole square. This is your dynamic equation using conveyance factors and section factors. So, what is the relationship or what is the criteria that will suggest that dy by dx has to be positive? For dy by dx to be positive, you can have two cases. That is, you can have two cases. Either the numerator in that relationship 1 by k n by k whole squared, this should be greater than 0 and 1 minus z c by z whole squared, this should also be greater than 0. If this is done, then this entire quantity, it becomes positive. Similarly, the entire quantity can become positive if 1 minus k n by k whole square, if this is negative, as well as 1 minus z c by z whole squared less than 0, if this is also negative, then also the entire quantity can become positive. So, there are two cases involved here for dy by dx to be positive. So, by giving this relationship, what do you mean by this thing? What does this suggest? So, before that, let me introduce you related to the slope of the channel. In the last class, we mentioned that there are 3 states of flow, right. You can have critical flow, you can have subcritical flow, you can have supercritical flow. One can easily do the laboratory experiments and all, you can see that there are these 3 states of flow. Now, based on these 3 states of flow, one can easily define the bed slopes of the various channels, in which category that bed slope of the channel is coming into the picture. For example, now let us consider a laboratory flume that is prismatic in nature. A prismatic laboratory flume, let us consider, it is having constant discharge Q. we can adjust the bed slope of the flume. So, what does that mean? So, you have a laboratory flume like this, say this may be made of glass, and you have the bed like this. So, this slope of the bed, it can be adjusted by tilting it, you can rotate it, this theta, it can be adjusted. So, it is giving you a steady discharge Q. Q is coming in, Q is going out of the flume. Say if it is a rectangular shape, you can easily draw it like this also, or if it is any other shape, you draw the appropriate shape. Now, the reason to show this flume is that, say if we say for this particular discharge, let us assume that initially uniform flow exists in the flume. Let us assume this thing. Let us assume initially uniform flow exists in the flume. Also, let us suggest that the normal depth of the uniform flow is above the critical depth. Therefore, the flow is initially flow is subcritical. Okay. So, if we increase the slope of the bed now, if we increase the slope of the bed, you will see that the normal depth of the flow in the channel, it will start decreasing. Say if this was the normal depth initially, and suppose if this was the critical depth computed for the particular discharge in this section, if this was the, then you will see that this normal depth, it will, if you increase the slope, it will decrease, that is the normal depth will decrease. Will decrease as bed slope is increased. So, it will decrease till, if you further go on increasing the thing, if you increase the bed slope, you will see that the normal depth will decrease and it will reach critical depth. So, for the given discharge in that uniform flow channel, for the given discharge, when you raise the bed, you have seen that the normal depth decrease, it is decreasing and it will reach the critical depth in that channel. So, that particular critical depth, whichever is there, whatever critical depth or whatever that depth of the flow that is abiding the critical flow condition, it has been achieved for a particular slope of the bed. So, for a particular bed slope, critical flow is achieved. So, that bed slope we are now going to say as S0C, that is the critical bed slope. So, this is called critical slope. Okay. So, if the actual bed slope, if it is less than critical slope, then that is called mild slope. You have seen that on further increasing in this thing, on further increasing the slope of the channel, the normal depth of the flow, it will further decrease below the critical depth. Then the flow becomes supercritical and the corresponding channel slope is called supercritical flow, that is subcritical slope, it is also called subcritical slope. And if S0 greater than S0C, then the slope is called steep slope or supercritical slope. So, one can see in the figure 3 different types of slope. I can just show it like this also, say mild slope, critical slope, steep slope, like that one can easily visualize for the same discharge. For the same discharge, you can easily visualize 3 type of slopes in the channel. So, like this one can categorize them. In addition to this, if the bed slope of the actual flow condition, if it is equal to 0, then those flows are called horizontal slope channels. Those flows are called horizontal slope channels. If S0, what happens if it is less than 0? If it is less than 0, your bed slope is, although the flow is like this, your bed, it is racing in the flow direction. So, it is having an adverse slope. So, such conditions are called adverse slope. This is adverse bed slope and this is horizontal bed slope. So, why we discuss first the bed condition is because based on these bed conditions, now one can identify different types of gradually varied flow in the channel. Let us see that. So, I hope you are now able to understand. Say there are mainly now the categories of bed slopes are critical slope S0C, mild slope, steep slope, horizontal slope, and adverse slope. So, these are the classifications of bed slope. Fine. Based on these bed slope, you can find different combinations of gradually varied flow. How can you identify that? So, let us come back into the equation, our dynamic equation S0 1 minus k n by k whole square by 1 minus z c by z whole square. So, in this equation, for we suggested for backwater curves, dy by dx is equal to positive, right. That is, you can have 1 minus k n by k whole squared by 1 minus z c by z whole squared greater than 0. So, the conditions we suggested that 1 minus k n by, if you recall them, it can be such that either 1 minus k n by k whole square should be greater than 0 and 1 minus z c by z whole square. This was one condition. The second condition was 1 minus k n by k whole squared less than 0, z c by z less than 0. So, these two conditions has to be satisfied, means either one of these two conditions have to be satisfied. So, that this entire quantity should be greater than 0. So, what does this physically mean now? For 1 minus k n by k whole squared greater than 0, or for 1 minus this quantity to be greater than 0, what should be the condition now? You need to have the normal depth y n by y, it should be less than 1. Then only this entire quantity can be greater than 0, or your normal depth should be less than the depth of the flow. This is one criteria, or you can suggest y greater than y n. Also, you need to have 1 minus z c squared by z square greater than 0. This means that, so this means that your y c by y should be less than 0, or your depth of flow should be greater than your critical depth. So, this means what does, you can now understand that thing. So, this means your depth of flow should be greater than critical flow. This implies subcritical flow, right. So, this implies subcritical flow. Also, your depth of flow should be greater than the normal depth, right. One situation for this is, one situation is the entire depth of flow is greater than both the normal depth as well as the normal depth is greater than the critical flow. So, this occurs in a subcritical flow, that is the subcritical flow occurs in a mild channel, that can also happen. So, may I beg pardon? I am just rubbing this portion. One situation you can imagine here is y should be greater than normal depth, y should be greater than critical depth. If I write that y is greater than y n greater than y c. So, this suggests subcritical flow in a mild slope channel. Another situation is, if your y, if it is greater than y c, which it is greater than the normal depth y n, then you can suggest that if this situation occurs, this suggests subcritical flow in a steep slope channel, that also one can easily witness. So, like this one can infer the things. Now, for a situation 1 minus k n by k whole squared less than 0 and 1 minus z c by z whole squared less than 0. For this criteria, you can suggest that your depth of flow should be less than normal depth as well as your depth of flow should be less than critical flow. So, critical flow. So, this means that supercritical flow exist. Supercritical flow has to be existed, then only you will get the backwater curve. So, this means the for example, if y less than y n less than y c, this implies supercritical flow in a steep slope channel. For your y less than y c, but less than y n, this implies supercritical flow in a mild slope channel. Right. So, similarly for the drawdown curves, how the dy by dx has to be negative and all, and subsequently further classification of the gradually varied flow profiles and all, we will discuss it in the next class. The quiz for today's lecture is as follows. Quiz, the first question is, what are the assumptions used to unify the dynamic equation for gradually varied flow using momentum and energy principles? We had used certain assumptions to unify both the equations, right. So, what are those assumptions? Please state them. Next question is, write the dynamic equation for gradually varied flow using the conveyance and section factors. Explain the terms in that equation. I am repeating the question. Write the dynamic equation for gradually varied flow using conveyance factors and section factors. Your third question. Now, using the dynamic equation in question 2, write the conditions for gradually varied flow to have backwater curves and drawdown curves, right? Or especially you write only the backwaters. What is the condition for gradually varied flow? So, you avoid this portion, only write gradually varied flow to have backwater curves. We have mentioned that conditions, you just enumerate them. So, the solution for the first question, for the you know that what are the assumptions involved here. It is a straightforward question. You can have the momentum correction factor as well as the energy correction factor approximately equal to 1, that is the velocity across the cross section is fairly uniform. This is one assumption. The second assumption suggested was the shear slope is approximately equal to the energy slope. Both are equated as the friction slope, where friction slope is computed using Manning's equation. The third assumption used is bed slope of channel is very small. Therefore, cos theta approximately equal to 1. Based on these assumptions, we had unified the dynamic equations for gradually varied flow. The second question, write the dynamic equation for gradually varied flow using conveyance factors and section factors. So, I am just writing the equation dy by dx, this is equal to bed slope into 1 minus k n by k, that is k n is the conveyance factor for normal flow, k is the conveyance factor for any existing flow, by 1 minus z c by z whole square. This is the dynamic equation using conveyance factors and section factors. So, you k n is the section factor for normal flow, z c is the k n is the conveyance factor, z c is the section factor for critical flow, z is the section factor for any for the existing flow, S 0 is the bed slope. Using the dynamic equation in question 2, write the conditions for gradually varied flow to have backwater curves. So, in that equation for backwater curves to exist, your dy by dx has to be positive. So, the first condition we suggested was that 1 k n by k whole squared should be greater than 0 and 1 minus z c by z whole square should be greater than 0. The second condition was 1 minus k n by k whole squared less than 0 and 1 minus z c by z whole squared should be less than. So, these two are the criteria for criteria that has to be used in the dynamic equation for the flow to have backwater curves. Okay, thank you.